when you get to the ultraviolet end of the spectrum, the classical physics is wildly out from reality. So, yeah, and the way Planck was able to resolve this was to assume that light was actually quantized.
Yes.
Which was basically the start of quantum mechanics.
So yeah, in classical physics this works a treat. So that's how you tell the temperature of a star. Now let's bring up Sirius. This is actually not exactly Sirius, it's a similar class star A1 spectral class. And this is an actual tracing. That goes up. So you can see that looks like a nice Planck curve. So that would be in line and keeping with it being a nice black body radiation. You go and find the maximum wavelength, which here is 4,500 angstroms. There it is going down there. You use your formula and it tells you 10,000 degrees Kelvin, which is Sirius. So if you look, put your spectroscope on the end of your telescope and your CCD camera and you plug in your computer and you tell it to print out one of these spectral energy distribution graphs, that's pretty much what you would see. Now, I've also mentioned these absorption lines tell you particular elements in there, but it tells you how many of the elements are there, and it talks about how energized those elements are. As you know, an element, neutron, a nucleus full of neutrons and protons with electrons all floating around it, and you give it energy, and those electrons get booted off. So if you see an element that's got its normal quota of electrons, you know, it's sort of a relatively low energy. But if you see an atom that's missing 2 electrons, you know, it's been highly energized. So a bit of energy's come along, injected some energy, and given 2 electrons the heave-ho. So they call it ionization. That's the word ionization. You see it, it just means 1 or 2 or more electrons have been given a shove out of there. And how that's happened, it's been energized. Just like these dips tell you what elements are there and how many of them, those little dips will also tell you how much ionization is going on of each element. It'll tell you the fraction of ionization of each element. In other words, it might say, look, 50% of your hydrogen's ionized there, 20% of your calcium's ionized here, and so on. So that gives you an idea of how much energy is going on there, which in turn tells you the temperature again. So there's 2 ways that graph will tell you the temperature of the star, and you correlate the 2 together. And it's that latter method is actually more accurate than your wavelengths. Yeah?
What's the y-axis?
Okay, the y-axis, yeah, good question. The gentleman's asked what's the y-axis. That's intensity or flux, how strong the light is. Good question, I should have showed that right up front, absolutely. They call it flux, or the intensity of the signal. Yeah. So you can see it's low here. So that's what it would look like in Sirius, and that's how you tell through spectroscopy the temperature, and of course I've also told you how you can tell the composition of the star as well. So now you know how to get its magnitude, absolute magnitude, its apparent magnitude, you know now how to work out the distance using those magnitude scales, you know how to tell what's made of, the temperature of the star. How about stars rotate? We all know most things like our sun, most things, almost everything in the universe rotates. How fast is that star rotating? Once again, the spectroscope comes to the rescue. Those little absorption lines that we saw back here, you see some are broader and narrower and stuff. As a star rotates, those lines get further and further broadened. It's because as the star rotates around, what the material that you're looking at is getting stretched away from you or pulled towards you, depending which side of the star you're looking at. So if the star's not rotating, that might just be a standard absorption feature. If you see in exactly the same particular spot, same wavelength, where a particular element is, and you know damn well it's there, but jeepers, that seems unusually broadened. That tells you that star is rotating around. There are formulas that will tell you how fast the rotation is according to how broad those spectral lines are. You can see here's a little spectral line. Once again, I mentioned that some places put colours in. Those colours are just being added in to make it look fancy, to keep you awake before you sleep in one of my books. So you can see this one's a bit broader with the dark absorption line, a bit broader here. And so the computer does a nice little print out. So how about the radial velocity? Velocity means how fast it's travelling. Of course, radial means travelling to and from, as opposed to something going in that direction. And you've probably all heard of the Doppler effects. It was sound, you all know it, like when an ambulance is screaming towards you, it's high pitched, because all the wavelengths, sound wavelengths are all getting squashed up as it moves, screams away from you, or some of it might be a police car, never mind an ambulance. Hopefully the police car goes past you, and when it does, you can hear the sound drop off and sort of change its pitch, because the wavelength of the sound wavelengths are getting further apart. Light's exactly the same. So you get the same spectral lines if something's sitting stationary. If something is moving away from you, they call it redshift, because all those spectral lines get shifted a little bit more towards the red end of the spectrum. And how do you know that's going on? Because all the spectrum lines are there that you would expect to see in that particular star. They're all same spacing that you normally get from a stationary star of that same type, but they're all just moved along to the red. That tells you that star's moving away from you. Similarly, if you get those same spectral lines, they're all matched up in equal proportions, away from here, so you know what you're looking at. But gee, that's odd. All these lines are a little bit pushed over this way. It's been blue shifted, that tells you that star radially is moving towards you.
Is the way influenced by the spin, the velocity of the spin?
Oh, with your broadening of your lines, tells you that, yes, correct, your rotation velocity. So it not only tells you, yeah. So it's, this one here tells you the broadening, tells you the rotation velocity, yeah. And these ones tells you the whole star itself, but it's moving towards you away from you. How about determining a star's size? How big is this star now? Well, it can be calculated or it can be observed. Calculations. Stefan Boltzmann, a couple of guys, they've got a law, an equation that said the luminosity or the power output of any star is 4 pi r squared. You might say, where did they get that from? The surface area. Recognise that? 4 pi r squared, the surface area of the star. That's that's the Boltzmann constant, physical constant, and there's the temperature, the effective temperature of the surface of the star to the power of 4. So if you've already worked out the temperature with your spectroscope, you can calculate from your magnitude. You look through your telescope, you know how far away that star is, you know how bright it is here, so you can work out the absolute magnitude, you can work out your luminosity, and there's your radius of your star there, so you can work it out with a formula quite happily. As I mentioned before, all formulas have implications. So what does that tell you? Is that if you double the size of the star, its power output's going to go up by a factor of 4. Weird. But look what happens if you bump up the temperature. You increase the temperature of the star, its power output goes up to a power of 4. Really rockets up. So Sirius, our friend Sirius again. Its radius is about 1.19 million kilometres. Once again, that means nothing to you. I don't know about you guys, it doesn't mean a lot to me. So you compare it with the solar radius, in other words, compare it to the sun. So it's 1.711 solar radius. So if the sun was yay big, it would be sort of yay big, or not quite double the size. Yes?
So why are they not half of the surface area and only half of the star's facing?
Yeah, I think that's the whole surface area of the star. Right, Cubit is what works out, yeah. But I know what you mean. That's the luminosity that's coming towards us. It's in joules per second towards us.
So you don't half it?
No, you don't. No, it's r squared. You don't half it. No, that's the radius.
No, I mean the surface area, because if only half the star's facing you,
Yes.
you halve the surface area to the formula.
Sure, yeah. It's actually like 3D. That's the formula that Stefan Boltzmann worked out. That is fits observations. So, yeah. Okay. Now, how about direct observing? This is Betelgeuse. You can, if stars are close enough and big enough, yes, you can. You know, the angular size is big enough to get your instruments and get a lock on it and determine its angular size. Of course, if you know its distance, you can work out its exact size. Often the moon or another body will occult, which means move in front of the star, or the star move behind it, depending on the way you look. But the bottom line is, if you time it from the beginning of the moon or a body that moves across that star, to that process called occultation, that will tell you if you time it, you can then work out the distance. You know the velocity of the moon, you can work out the distance it's travelled, and you can then project back the distance of the star, and that'll tell you how big the star is. The other scenarios where you get binary systems, if they're sort of relatively straight on to us, in our line of sight, both stars, you'll see the light curves. As one ducks in front of the other, light curves dip, and that also they can work out from there the size of the star, depending on how much the light dips. So those are three direct ways you can actually work out the size of the star. And once you get the size of the star, you know how to work out the temperature, then you can work out luminosity, and you can see it. You know, once you start getting that ball rolling, you can very quickly get to know the full parameters of the star. You've only got to measure about 2 parameters, and you've got below. Okay, so here's back to our night sky. So here is Sirius sitting up in Canis Major. Here's Betelgeuse down here. This is a southern hemisphere view. So there's Betelgeuse. So you all know Betelgeuse up in the sky. So where you see the pot, you look up to the north, you see the pot in the sky, and just below it you see that big orange ball of a star. Go and look for it tonight, and you go out, that's Betelgeuse. Look at the size of Betelgeuse. It's a red supergiant, which we will talk about in one of the talks on stellar evolution. But look at the size of it. So here's our sun, that tiny little dot. There's the orbit of Mercury, the orbit of Venus, Earth, Mars. It goes just beyond the orbit of Jupiter. That's how big it is. You hop in a spaceship, head from the sun, keep going out, past Mercury, past Venus, past Earth, past Mars, past Jupiter. You're still inside Betelgeuse, the star. It's huge. Or so you thought. This is lovely comparison stars. So here's the planets here. Then here's our sun. There's Jupiter. Look how big Jupiter is. There's Jupiter. That's the sun. Dorsal mass. There's Sirius, about 1.7 solar radii size, a bit bigger. And you keep moving up. So there's Sirius now. Sirius looks really small now. Look at that. Imperial Pollux, Arcturus, Aldebaran. And then you get Aldebaran. Look at the size of Aldebaran compared to Sirius, compared to the sun. And look at that, that's Aldebaran there. Holy moly. And there's Betelgeuse. How many did you come from Moroni Bay, the North Shore, Antares Place at the Millennium Centre? That's Antares. So Antares is the main star, the big red giant that you see sitting in Scorpio, the scorpion-shaped constellation in wintertime. So that's Antares and Betelgeuse. When you see those guys in the sky, whoo, you take your hat off. Those guys are biggies. There's even bigger stars. Look at these guys getting dwarfed by these ones. So it gives you an idea of the wide range of the size of stars.
Notice the one, can you go back to that, Chris?
Sorry, what's that?
Can you go back to
Yeah,
that
yeah,
slide?
sure.
You notice one odd one out of those stars?
What's the odd one out?
The blue one.
Oh, right, yes.
Yeah, so that's,
Oh, yes, yep.
the others are all, the big ones are all red giants. But that star in the large Magellanic Cloud is a massive supergiant, incredibly hot star rather than a cold star like the red giant.
Yes, you have a question?
But that's not like, but why isn't there UI scooted on the list?
Why isn't, sorry?
There UI scooted on that.
Oh, that's a star. Yeah, they've just picked well-known stars here. They've just picked, yeah, haven't put all stars here. Yep, it's good that you know your name for some of your stars. That's impressive. Very good. So, what have you learned tonight? You're going to take home and tell the family? CCD, digital imaging, is what they use to accurately measure brightness or apparent magnitude. It's trigonometry or parallax, the principle, and stars that pulse, called variable stars, that are used to measure distance within and sort of around the Milky Way galaxy. Spectroscopy is one of the main instruments they put on the front end of the telescope. That measures agents. From there you go to measure the temperature and the composition of the star. You're able to measure if it's rotating, in which direction, and how quickly.
It's actually not on the front of the telescope, on the back.
Well, yes, you've got the, yeah, it's in the front of the instrument, between the telescope and CCD, yeah. And it's calculations and observations you can measure the size. So you can get a good idea, so how do they predict or tell you all these properties of Sirius? That's how they do it. So, call to action, next clear night, later tonight or tomorrow night, go out and look for Sirius and Betelgeuse. You know where to look for them now. Tell someone, hey, got your temperatures? Sirius about 10,000 degrees, Sirius I think about 3,500. Quote the distances and the size, they'll be very impressed. And then you can explain, how they'll probably ask you, well, how do they know that? You better tell them what they know. Most people have lots of fun. I hope you've enjoyed measuring stars. Now the movie time, I realise some of you might have to go. We sort of, I was talking far too long. But this guy's really worth listening to, Alex Filippenko from the University of California. And he gives a 30-minute lecture, and it's all about the intrinsic brightness and luminosity of stars. And it complements the talk and just brings a few other little concepts together. It just ties it all in quite nicely. You can stop